So today I want to introduce centripetal force, and it's actually really neat because it's very different from what we talked before. And I'm going to eventually relate it to two-dimensional forces, so that's why I'm bringing it up. Most of us probably don't really think of it as different from velocity or a typical normal force, but it's very different. So remember, force is something that causes a mass to accelerate. But what is acceleration? Well, acceleration is change in velocity over time. Most of us, when we think of velocity, we think of magnitude. So when we look at this, remember, velocity is a vector, has both magnitude and direction, and pretty much for the last 3-4 weeks, we've been talking about what happens when magnitude changes. Now we want to talk about what happens if direction changes. So when you look at these pictures, most of us probably haven't done the last two or even the spaceship one, but most of us has probably been on a ride like Dumbo, where you're just sitting in a ride, and it'll speed up initially, but once it's going, it's going to move at a constant speed around in a circle, but you're still experiencing a force, and we'll talk about that, centripetal force versus centrifugal force. You're still feeling a force because something's keeping you moving in a circle. If we remember back to Newton, inertia, we want to stay at a constant velocity, right? What does that mean? If there is no forces acting on you, you want to keep on moving. Well, that means constant velocity, which means constant speed and constant direction. So if you're moving in a straight line, you want to continue moving in the straight line unless something stops you from moving in that straight line. So that's what centripetal force is. Something that stops you from moving in a straight line. Okay, here's an example. You have planets revolving around the sun. If it wasn't for the sun, these planets are going to move in a straight line. And what happens is it's going to experience gravity around the sun. And that gravity is going to pull it towards the center. And what's neat about it is that here, at let's say this point of the Earth, right here, the gravity is going to be this way. But as it rotates around, it's going to be now here. So you'll see as it rotates around the sun, the force of gravity changes. So that's why this thing, or Earth, is experiencing velocity even though it's going at constant speed, because what's changing is the direction. So something's pushing you towards the center. All right. Gravitron, or something similar to it, looks something like this. So you might have been on a ride like this before, and it's quite fun. What it does is it spins you around, and this one's already starting to do its angle. But normally, if you just imagine you're spinning horizontally, what's going to happen is your body, let's say this person right here, has a velocity, right? And according to inertia, it wants to go in a straight line. It wants to come out of the circle. But the force here, the ride itself, is keeping the person moving in a circle around and around and around. So what's happening is, in this case, instead of gravity, it's force normal. So force normal is pushing on the person in. So what's cool is if you spin fast enough, this force normal gets so big, it could overcome gravity, so you can start spinning it higher, higher, higher. So the fun part of this ride is it's going to start tilting, and you're going to still stay stuck to a wall. Gravitron's a little bit different. If I fast forward to that one doesn't tilt, but what's cool is that the bottom goes out on you. You can see from this guy, he started standing on the wall because it's spinning so much, it kind of acts like gravity. So it's pretty neat. You have something like that. So, and what I have here is that it's not a real force. What do I mean by that? So in this one, you have gravity that's keeping it in a circle. Here you have force normal keeping it in a circle. So what I mean by that is centripetal force is not a force. Something else is providing that. So some other force is providing centripetal force. So in previous was gravity, here it is force normal, and then here, if we look at the car, and then you can watch the video later for yourself, it's the friction. So the friction is causing the car to turn. So that one's also causing the centripetal force. If you look at it, if this is when you're on ice and then they turn the wheel and nothing happens, well, it's because there's no friction. So there's no way the car could be pushed towards one direction or the other of the circle. Now, let's talk about equations. Like I said before, I never need you guys to really understand how, I guess, what's it called? How it's derived, but it's good to understand where it comes from. So I did post up something done really well by Khan Academy. They did a really good job of showing what's going on. So I'm going to cut and paste from them really quickly. Control V. There we go. And I'm going to steal their picture. So here you have two things, and you'll notice here is a circle, and then here's our vectors. And what they want to show us is that the relationship between all these terms. So here you have the center of the circle, here's the radius, here is, oh gosh, I can't remember the words for it. Give me a second. Think. One's an arc, and the other one's the chord. Ooh, I remembered the chord. So change in R is the chord, change in S is the arc. And then it wants to show you where the velocity is with this, how it's related. Okay, so here's the velocities and here's this. And then what they want to show you is that you have two triangles. And these two triangles are much more similar than you think. Okay, so what I want to show you is that eventually is change in V over V is equal to change in S over R. Okay, so change in V over this is the same as change in S over R. And the reason is because these angles are very similar. Okay, as we are getting very close together. So what, instead of having a big one, let's say the angle is like right here. So then this will get really close together, and what's going to happen is this V is going to be pointing towards center. And this angle is getting small enough so you can have this relationship that they have right here. What we could do is we could divide both sides by t. Let me make sure. Actually, let me solve for V first. So I'm going to move the V over to the other side. Change in S, V over R. And then what I want to do is divide both sides by t. And the reason why I want to do that is because now this is equal to A. So this is equal to A. And then I have change in S. There's a fly in here. Change in S over change in T times V over R. So we have that. Now when we look at this, you have a change in velocity. This is actually called angular velocity right here. Angular velocity. So what's happening is that over time, you're going to gain this arc, right? As it spins around a circle, you're going to get that arc. So that's change. So we could kind of substitute this as a V. So AC equals V times V over R. So centripetal acceleration is V squared over R. So it's kind of weird, but that's just how it is. And then remember, force is equal to ma. So it's just centripetal force is equal to mass times V squared over R. So here's our two equations. Let me rewrite it over here. Hopefully it made sense. If not, I'm going to post up a bunch of references and we could go over it. But you have AC is equal to V squared over R. And then you have FC equals mv squared over R. So those are two equations. You don't have to know how we get there. I always try to show you. Some of the math out there on the internet is much easier. I like how Khan Academy did it because they kind of avoided limits. Other places which do a better job of explaining kind of the relationship between these two, but it requires limits, and I don't think we know that yet, and I want to keep it algebra 2. So I kind of skimmed through it, but the reason why it's more similar is because of the limit property. So it's kind of like the whole derivative, where do derivatives come from. As you're going limit closer and closer, you're going to have derivatives. So if you want, I'll be happy to kind of go over the calculus part with you guys if you need to. But for now, let's just keep it simple, keep it like that. So those are my equations, FCAC. Now remember, this isn't a real force. What I mean by that is something else is providing this force. And then so now what you could do is, not only is Fg equals to mg, but it's also equal to mv squared over r. So that's pretty cool. And we'll kind of get that to the very end. I like you guys to kind of watch this a little bit later. I think it's pretty cool if we ever drive in water or snow. And then we'll kind of get to that after we talk about gravity. But before I get there, I want to talk about centrifugal force and the difference between that. So you have something called a centrifuge. And we probably used it before in chemistry, where you spin something really, really fast and all the heavier things fall to the bottom, all the lighter things go to the top. Or even when you're in a car, if you turn the wheel really, really hard or fast, your body wants to move straight, but since the outer part of the car is turning, you're going to feel the opposite direction. Even so, the car is moving to the right, you're feeling you're getting slammed to the left. And that's because your inertia wants to go straight. So let's say this is you. Top view. Here's you sitting in your car. So here's the car. Here's the steering wheel. I won't do the steering wheel. So here's you in the car, top view. So I guess there's your nose, and then your legs, and then your arms. There we go. Kind of weird. Anyway, the car's moving this way. Now, what's going to happen is as the car turns this way, you still want to go straight. So even though the centripetal force is this way, you feel you're getting slammed this way. This is what you feel. So what you feel is the centrifugal force, and this is the centripetal force. So that's the difference between the two. So in a roller coaster ride, if the roller coaster is going to the left, you feel like you're getting slammed to the right side of the wall. And that's just because of inertia. You want to move forward. Now, gravity. So why are those things actually pretty relevant for us? Well, you'll notice that I'm going to have videos posted up for Space Odyssey. I think it's Elysium. That's the one with Matt Damon. And there's another one with Matt Damon. And all these movies you see, let me go back to this one, a spaceship with a circle. And when you look at it, these things are rotating around like this. And let's say you're a little person right here. So what's going to keep you moving in that circle is, again, force normal. But they kind of design it so that it's pushing on your feet. So if you have the right radius and the right spin, you're going to have artificial gravity based on centripetal force. So we're going to spend, I think, the next few minutes kind of talking about that, watching the movies and discussing it. So hopefully that makes sense. And that's it.